We're going to talk about graphing rational functions today, and you should have done this last year. So hopefully this is a review, and it is a little bit tricky. So let's say I had x minus 4 divided by x squared minus 5x plus 4. And I wanted to graph that. Well, I need to factor the denominator. And I get x minus 4 over x minus 4 times x minus 1. Okay. Are there any domain restrictions in this? Yes, x is not allowed to be what two numbers? 4 and 1. Why not? If I plug 4 into there, I get 4 times, or sorry, I get 0 times 3, and 0 times 3 is 0, and I can't divide by 0. If I plug 1 in, I get negative 3 times 0, which is 0, and then I'm not allowed to divide by 0. The interesting thing is, if I plug 4 in here, I get 16 minus 20 plus 4, which is 0. If I plug in 1, I get 1 minus 5 plus 4, which is also 0. Okay. Now, what happens at x equals 4 and x equals 1? Well, that depends on the function. We know that x cannot be 4 and x cannot be 1. But what do those places look like on the graph? And the answer is it depends. So I have a graph here. Notice how I have an x minus 4 on top and an x minus 4 on bottom. If a factor in the denominator cancels, we call that a hole on the graph. So x equals 4 is a hole. Excuse me. What does it mean to be a hole? So the graph's coming around, 1, 2, 3, 4. It jumps right over that point and keeps going. Okay. What's the other option? If it's not a hole, what else can happen? You guys remember? So let me back this off just a little bit. The other option is called a vertical asymptote. So, if a factor does not cancel, then there is a vertical line that runs through the graph that the actual curve never touches. So, at 1, I have this dotted line, and the graph never hits it. So it could look something like this. Not quite sure yet. Okay, so that's the first thing for today. If a factor in the denominator cancels, we have a hole. If a factor in the denominator does not cancel, then we have a vertical asymptote, and we're just going to abbreviate that from now on as x equals 1 is a VA, vertical asymptote. Okay. What about horizontal asymptotes? Because rational functions often have horizontal asymptotes, which is a dotted line that's horizontal that the graph never touches. So this graph could look like this and have a hole at 4, right? Or it could look like this with a hole at 4. There are a lot of different combinations, and it sort of just depends on the graph. Okay, so how do we find horizontal asymptotes? Well, it's actually pretty easy. If the degree of the numerator is less than the degree of the denominator, then y will never equal 0. Okay, which basically means if there's a higher power x in the bottom than on the top, then your horizontal asymptote is at 0. Now, why is that? Well, let's look at x to the fourth plus 6x to the third minus 8x squared plus 2x plus 1 over x to the fifth plus 4x to the fourth minus 6x to the third plus 2x squared plus 1x minus 3. Okay, so what I want to know about this is what happens on the far edges. Okay, so what happens when I go really far to the left or really far to the right? Well, I draw my graph, and I don't really know what happens in here, but clear over here, what happens? Well, my x values are huge. Right? So let's say 10 billion. If my x value is 10 billion, what happens to the graph? Well, if I'm plugging in 10 billion for x, what effect does this plus 1 have on the graph? If I'm doing 10 billion to the fourth plus 6 times 10 billion to the third minus 8 times 10 billion squared, what effect does this 1 have? If I have a number that's so big it doesn't fit in this room, and I add 1 to it, have I really changed it? Not very much, right? So can you see how that plus 1 is totally insignificant when compared to an enormous number? Okay, well, let's do the same reasoning with this. If I'm plugging in an enormous number, is 2 times that number anywhere near that number to the fourth? Do you guys understand that? So if I start plugging in humongous numbers, then this number is really large. And this number is pretty insignificant. And this number is pretty insignificant. And in fact, they're all insignificant. 10 billion to the fourth is huge. And which grows faster? Something to the fourth or 6 times something to the third? Well, for a while it will, right? Until this number gets bigger than 6. So it turns out that none of those numbers tend to matter very much when I am plugging in enormous numbers. Does that make sense? An enormous number to the fourth is way higher than any of the others. And you know when your calculator does scientific notation, like 3.8 e to the 25th? If I had 3.8 e to the 25th and I add 10,000 to it, is the calculator even going to register that? No. So what's happening is, when I get clear out here to the right side, none of these matter as much as the first one. Well, what about the denominator? The exact same thing happens. When I get numbers that are big enough, this number won't even show up on the calculator. Nor will this one or this one or this one or this one. So that leaves us with x to the fourth divided by x to the fifth. And this is a really important concept right here. What is x to the fourth divided by x to the fifth? It's 1 over x, right? Because it's the same number. 10 to the fourth divided by 10 to the fifth is 1 over 10. Okay? And what happens when I take a number to the fourth and I divide it by a number to the fifth? Well, it simplifies down to 1 over x. Right? Well, what is 1 divided by an enormous number? A very small number. And if I do 1 divided by infinity, I'm actually approaching 0, right? The larger the denominator, the closer I get to 0. Does everybody understand that? So if I plug in a huge number, then this number is so close to 0, I can't tell the difference between it and 0. Okay, now that's a really long explanation, but do you see what's happening? The further I go to the right, the less and less these have an effect on the graph. And I'm basically simplifying down to that. And x to the fourth divided by x to the fifth is 1 over x. And 1 divided by an enormous x is essentially 0. So what that means is I have a dotted line at 0 that the graph never touches. So it could look something like this. Okay. What if I change this fifth to a sixth? Now it's 1 over x squared. And what is 1 over x squared when x is really big? It's 0. It's even quicker to 0 than it was before. So what if it was x to the seventh over, or sorry, x to the fourth over x to the seventh? Then this would be a 3, and the same thing happens. So the first thing you need to know about range today is if the bottom is bigger than the top, then y can never be 0. What if they're the same size? So let's have x to the third minus 6x squared plus 2x minus 1 over x, or let's do 5 and 3. Okay. What happens when I start plugging in really, really big numbers? Well, if x is huge, then these tend to not matter. And do you guys understand that concept? Do you see that eventually 5x to the third is so much bigger than the rest of the equation that we don't need the rest of the equation? Now, in the middle of the graph, we certainly need all of it. But on the edges of the graph, really only the first one matters. Okay? And then on the bottom, we can also cross off everything but the 3x to the third. What is 5x to the third divided by 3x to the third? Well, 5 times a huge number to the third divided by 3 times a huge number to the third, all of those huge numbers are going to cancel, right? So this cancels that, and I'm left with 5 over 3. Now, are we ever going to equal 5 over 3? No, because that other stuff still exists, but it's just really, really small in comparison. So if the bottom exponent and the top exponent are the same size, then your HA, your horizontal asymptote, is at the fraction created when you divide the leading coefficients. Okay? Let me see if... Okay, so we've done bottom is bigger than top. If the bottom is bigger than the top, then your HA is at 0. If your top and bottom are the same size, then your HA is at the fraction of the leading coefficients. What if your top is bigger? What if I have 4x to the fifth, and none of that other stuff matters right now, so I'm not even going to write it. And I divide that by 6x to the fourth. Well, what happens when I divide 4x to the fifth and 6x to the fourth? I get 2, well, that's not a 2, 2x over 3. Does everybody understand that? Well, all but one x cancels, right? Okay, you sit behind Bell. So what does that mean? Thanks. That means there is no horizontal asymptote. The asymptote is actually a slanted line. So this graph has a slanted line like this with a slope of 2/3. So your graph might look something like this. Okay? The fraction of the two leading terms is 2x over 3, and this is the equation of the line that the graph never touches. Actually, it's the slope of the line that the graph never touches. Well, that's a really good question. Where do we start? Oops. Where do we start that line? And the answer is, I'll show you how to do that later. But but it could be anywhere around here. It just depends on the function. And I'll show you how to do that, but certainly not today. Okay. Well, what if the top is even bigger? What if I had 2x to the 5th and x to the 3rd? Well, that simplifies to be 2x squared. So that has it doesn't have a slanted asymptote, it has a quadratic asymptote. Oops. So, and again, I don't know where it hits the y-axis, so I'm just going to guess. So your graph might look like this. You will, but it's actually pretty easy. I'll show you. Well, once we're done with figuring out the asymptotes, then we'll go on to graphing. Okay, so if I have x to the 3rd over x to the 5th, I have an HA at y equals 0. Okay, whenever the bottom is bigger than the top, your HA is at 0. Why? Because that simplifies down to 1 over x squared. And whenever you plug something into 1 over x squared and it starts to get really, really large, you get closer and closer to 0. Will you ever get to 0? No, never. But you'll get so close eventually you can't tell the difference. Okay? If the top and bottom are the same size, so x to the 4th over 2x to the 4th, then we have an HA at y equals 1/2. Because that is the fraction I get when I divide those. Okay? And if the top is bigger, so let's say 3x to the 4th over 2x to the 3rd, then I don't have an HA. I have a slanted asymptote at 3x over 2, and that's just the slope. The y-intercept we don't know at the point, but at this point. What if I had 3x to the 5th over 2x to the 3rd? What kind of asymptote would I have? Well, what is 3x to the 5th over 2x to the 3rd? It would be 3x squared over 2. Now, that you will see equations like that in this class, but you'll never have to graph one of those. I don't think any of those show up on your graphs. But your asymptote could be an x to the 3rd or an x to the 5th or whatever. Anything larger than that. Okay, so turn to page 308. All right, so actually, let's go back a page. Let's go back to 307. So I have x plus 1 over x squared minus x minus 6. Does the bottom factor? Yep. X minus 3 and x plus 2. Okay. Does this graph have any holes? No. Why not? Because none of the factors of the denominator cancel. Does this have any VAs? So this is none. Does this have any VAs? X equals 3 and negative 2. How did I know both of those are VAs? They are factors of the denominator. And we know x is not allowed to be 3 or negative 2. And that's the domain, right? The domain is all real numbers, but x is not allowed to be 3 or negative 2. Does this have a horizontal asymptote? Does it have a horizontal asymptote? Yes. Where? At 0. Why? I divide these. What is x divided by x squared? 1 over x. And what happens when you plug big numbers into x? You get small numbers for your y. Okay? So this has an HA at y equals 0. And that's in fact the range. The range is all real numbers, but y is not allowed to be 0. So your wholes and your VA will tell you your domain, and then your HA will tell you your range. Okay? Well, most of the time. So look on 307. Do you see that domain? Negative infinity, comma, -2, union -2 to 3, union 3 to infinity. That's not how I would write it. I would just say all real numbers, but x is not allowed to be 3 or -2. That's way easier. Okay, turn the page. Well, I'll show you. They're different problem sets, but I'm just teaching you the basics for right now. So example 2. 3x over x squared plus 9. Okay, does the bottom factor? Yes, into x what? X plus 3i and x minus 3i. So when does the bottom equal 0? It doesn't, because the roots of the quadratic are imaginary. So what do you think the domain of this function is? Go the other way. Everything's the domain. So the bottom has no holes and no vertical asymptotes, which means every x value works. The domain for this is all real numbers. Now, what about the range? Well, let's divide this. What is 3x over x squared? 3 over x. And what happens as you plug in humongous x's? We get closer to 0. But wait, this time it's 3 over x. Does that matter? No. 10 over x, 1 over x. Any number divided by infinity is 0. Right? 10 divided by infinity, still 0. Except for infinity divided by infinity. That's a little bit complicated. Sometimes it's 0. Sometimes it's 1. And sometimes it's infinity. Yeah. Yeah. That's a calculus problem, though. We don't do that in this class. Okay. What about, so this has an HA at 0, y equals 0. And that one, the range is a little weird because some of these graphs could actually look like this. Zero, but well, yeah. So your problem set actually just says state the domain. You don't need to state the range, but we do know that it has a horizontal asymptote. Okay. Now we need to look at, see where it says your turn under 308? X squared minus 4 and x plus 2. Can we factor the top? X minus 2 and x plus 2 over x plus 2. Those cancel. So x equals -2 is a whole. And what about vertical asymptotes? Are there any factors in the denominator that do not cancel? No. So there are no VAs. Does this have an HA? When I divide the leading coefficients, I get x. And what is the graph x? A slanted line. So this has a slant asymptote at 1x. Yeah, there's a lot to remember. So, what is the domain of this function? All real numbers, but x is not allowed to be -2. The range is probably all real numbers. Well, so it has a slanted asymptote like this. So the range is kind of complicated because it might look something like this. Or it might look Oh, great question. Can the graph cross the asymptote? In the middle it can, right? This trick only works on the far right and the far left. So it can cross the asymptote a whole bunch of times, but on the edges, then it follows this pattern. Does that make sense? Yeah, if there's a hole, the graph is just curving around wherever it is, and it jumps over that one point and continues. Yep. Well, you don't have to find range. Yeah, it doesn't ask you for the range because there's a good chance. So if your graph looks something like this, you might have a whole big gap in there of range that you're missing. So range gets kind of complicated. So a lot of the time we don't worry about the range. Okay. So example 3. 5x plus 2 over 6x squared minus x minus 2. And they factored it for us, which is nice. 5x plus 2 over 2x plus 1 and 3x minus 2. Does this have any holes? Do any of the factors of the denominator cancel? No. Okay. Does it have any vertical asymptotes? Yes. Where are the VAs? X equals -1/2 and 2/3. So if they cancel, it's a hole, which it didn't. If it doesn't cancel, then it's a VA. Okay. Does this graph have a horizontal asymptote? Yes. I divide the leading coefficients, and I get 5 over 6x. That is essentially 0, because if I plug really large numbers in there, the 5 and the 6 don't even matter. Right? 5 divided by 6 by an enormous number is still 0. Okay? So this has an HA at y equals 0. What if it was 5x divided by 6x? Where would the HA be? It would be at 5/6. What if it was 5x squared over 6x? Where would it be? It would be slanted at 5x over 6. That's the slope of the slant. Okay? All right. So, all right. So, look at 321. The first set, find the domain. The domain is really easy. How do you find it? You look at the denominator. You set the denominator equal to 0, and then you find the domain restrictions. Okay, 9 through 16. Find the vertical and horizontal asymptotes. Vertical's easy. Oh, I also want you to find holes, if there are any. Okay. Factor the bottom. If it cancels, it's a hole. If it doesn't cancel, it's a vertical asymptote. Horizontal asymptote is easy. If the top is smaller than the bottom, then the HA is y equals 0. If the top and bottom are the same size, then it still has an HA at the fraction of the leading coefficients. And if the top is bigger than the bottom, then it's a slant or a quadratic or something larger. Okay, turn the page. Oh no, that's it for today. Yep, that's it. So your assignment is 321, 1 through 16 all. 1 through 16 all. And tomorrow we'll talk about slant asymptotes.